everyone, so I want to talk about the last thing with the multi-mass system. We will return to this later, especially once we learn about some of the more other unique scenarios, such as inclined planes. But the other thing that I want to talk about is what's called a modified Atwood machine. So we already talked about the regular Atwood machine, where you have one object hanging from a pulley and another object also hanging from a pulley, and the whole thing just goes up and down. Now what we're going to do is we're going to take that object, and one of those objects at least, and put it on a flat horizontal table. That is what's called a modified Atwood machine. You have one object that's hanging off the edge and the other object that is sitting on top of the table. And we're going to end up doing literally the exact same stuff. Again, the setup is the exact same. What we're going to do is draw the FBDs, include the direction of acceleration, F net equal ma in multiple ways, the exact same way. And we have to make sure, though, that every single time we are looking at only the forces acting in the plane of acceleration. Those are the forces that matter, not up and down, left and right. Whatever direction is, whatever force is in the plane of acceleration, that's what matters. Um, Later on, I can actually make this question a little bit more difficult, because now that we have it on one of the blocks on a table, I can add friction to it. I can actually have the other end of the block touch it, hanging from another block, so I can have three blocks on it. I can put that block on an incline. I could put that incline with friction. I can put both of the blocks on an incline. I could just go extremely crazy with it and just keep doing all these variety of different multi-mass setups. But the crux of the matter is that regardless of how it's set up, they all are set up the same way. All right. So here's the first modified Atwood machine. So pause the video, work itself, and we'll go in a second. All right. So again, what we're going to do is set up the FBD. Now we have M1 being on the table, M2 hanging. This is a frictionless setup. So when I do my FBD, I'm going to have the force of gravity going down, the normal force going up, and tension going to the right on block 1. And it's also going to be accelerating to the right. Block 2, it's got gravity going down, tension going up, and it's accelerating downward. All right. I'm going to do the same thing that I do. I start with my F net equals ma. Here is where it gets a little bit different. Just a tad though. Again, the forces are in the plane of acceleration. This block stayed the same. This still goes in the direction of acceleration, so that's positive. This one's negative because it's going opposite. But then when I look at this block, I'm not looking at these two forces because those are not in the plane of acceleration. My acceleration is horizontal. So I'm looking at horizontal forces. The big takeaway is that the pulley changes the direction of positive for the two objects. So when I set this up, I get Fg2 minus Ft plus Ft. Again, this ends up dropping out the tensions, which is exactly what we expect when we look at it as a system, one complete object. So I end up getting the 50 Newton weight of the hanging mass, and then the total mass. So even though only one of them is hanging, again, the definition of the M in F net equals ma is all the masses that we're looking at that are moving. M1 and M2 are both moving, therefore I'm combining their masses to 13. So 50 divided by 13 is 3.85 meters per second squared. From here, everything else ends up, again, remaining the same. We want the net force on both M1 and M2. For M1, I plug my numbers in, 8 times 3.85. I end up getting 30.8 newtons to the right. And then for block 2, I just do the same thing but with 5 kilograms as my mass, and I'm getting 19.25 newtons down. All right, nothing crazy. When I get to part C, I'm looking for the tension force. The nice thing here is that this is one of the reasons why I made the comment before that when you are looking for the interactive forces, you should try to look for the forces that are on the FBDs that are simple, the ones that have the least forces to talk about. If I look at M1, there's only one force acting on it, tension, in the direction of acceleration, that is. So tension turns out to be equal to the net force. We already know what the net force is, 30.8. So my tension is 30.8 newtons to the right. So this is what I always recommend doing. Uh, if neither one is good, like both of them had two forces, I would normally pick the one where the tension is positive. Again, just to make my life a little bit easier. But you can choose whichever mass you want. Looking at M2, this one again, same thing as we did in the regular Atwood machines. We have weight going down, so it's positive because it's in the direction of acceleration, and we have the tension going up, so it's negative. Plug my numbers in, I end up getting that the tension is 30.75 newtons up. Again, the numbers are extremely close, so that shows that my math is correct and my numbers make sense. All right, here's the next one. Pause the video work itself. I'm going to go in a second. All right, now we're including friction. So it's actually the exact same setup, same numbers, everything all around, but now the friction, there's friction on block one. So this is going to slightly change our numbers. So it's actually going to be nice to compare the numbers that we get here with the frictionless setup. So when I do the FBD, I still have the force of gravity going down and the normal force going up, and I also have tension going to the right, but I also now have the friction going to the left. And my net force is still, my acceleration is going to the right cell. The second block ends up being exactly the same. So because of this added friction, when I do F net equals ma, now the friction has to be included in here. Tension still drop, so now my net force is essentially the force due to gravity of the hanging block, which is still 50, but now I have to figure out the force of friction. Now I didn't do the work here, but recall that we're using the equation mu Fn. Since we're talking about block 1, Fn in this case is going to be equal to the weight of block 1. So this is going to be the mu, which is 0.34, times the weight of block 1, which is 80 newtons. So I do that. My total mass doesn't change because it's still 13 kilograms moving. So my acceleration goes from the original 3.78 or whatever to 1.75. So a very drastic decrease in the acceleration. Going to part B, finding the net force. Again, F net equals ma. Nothing crazy. We plug our numbers in. We get M1, the net 1 being 14 newtons right, and net 2 being 8.75 newtons down. Again, compare this to the number 32, and we got a drastic decrease in these numbers. Last one is part C, finding the tensions. So unlike in the previous question where we had tension being the only force on block 1, that's no longer the case here. Now we're going to have friction. So the net force is going to be tension minus friction. The net force is still 14. And friction, like we said, it was we already got it before. I didn't write the number, but it was 27.2 newtons. And when we do that, we get that the tension 1 is 41.2 newtons to the right. Similarly, if I do it for block 2, it's literally the same setup from number 32. Plug our numbers in, and we get 41.25 newtons up. Again, the numbers are very, very close, off by only 0.1 essentially, or technically 0.05. And that's pretty much the modified Atwood machine. Like I said, there's really not much of a big difference. It just allows me to start adding in more forces, so it's not the exact same thing every single time. As I said, regular Atwood machines pretty much are the same setup every single time, but now with the modified Atwood machine, I can start including in friction. I could place a block over here on top of this and have it so maybe this slides off. I can attach a block to the other end, so then I have 3 blocks connected by a string. I can set it up so that one of the blocks is on an incline. And like I said, regardless of how I set up the problem, the setup is always the same. So you'll probably see one of these in the next video when I start talking about inclined planes, and we'll see how that ends up being brought in. There's two more questions, which are going to be conceptual based questions. Now, they're going to be good if you are able to if you could just do the calculations and test it out. Otherwise, try to think about it conceptually. All right, so pause video, work itself, and we'll move in a second. All right, so they want us to say what happens to the acceleration as we increase m1. Now, uh, there's really three options. It either increases, decreases, or stays the same. That's it. But we need to figure out what's going on. Now, I can set up the equation for this. I can try solving this algebraically, doing the same thing I did before with there being a tension here and a tension here, and this being m2g, and trying to solve this to figure out what the acceleration is in variable terms, and then just alter m1 and see what happens. But I can change things a little bit differently. I can make it a little bit simpler. We know that the acceleration is going to be based off of the equation F net equals ma, where F net is going to be the sum of the forces acting on this, and the mass is all the masses combined. When this is a frictionless surface, if we go back to question 32, the only force that is acting in the direction of acceleration is the force of gravity of mass 2. So the net force is strictly related to and controlled by m2. So increasing m1 does not affect the net force, but it does affect this mass, the mass that's moving. Now that I increase m1, I'm increasing this value. This number stays the same, therefore an increase in mass will end up causing a decrease in acceleration due to their inverse relationship. Now, how would I explain this? If I wanted to put into scientific words in a more physics appropriate AP style, the way I would say it is that increasing mass 1 increases the total inertia of the system. Remember, the inertia is how resistant the system is to the change in motion. So increasing mass 1 only increases the total inertia of the system, meaning that it requires more force to get it to move, to change its motion, to accelerate it. Since the net force is acting on the same as since the net force acting on the system is remaining the same, that means that this increase in inertia must result in a decrease in acceleration. So this would be a very appropriate AP style answer. You might want it a little bit more tailored to how I said it. As I said, that it requires more force to get it to accelerate. Therefore, if the force stays the same, the acceleration decreases. You probably want to make that comment, but for the most part, these are the two main statements. Increasing the mass increases the inertia. The net force remains the same. Therefore, acceleration decreases. Part B, now we're looking at mass 2. Well, if I do the similar thing, looking at the net forces that are acting on the system, I'm not going to erase this. Here, we said this before, that this force, this net force, is being strictly controlled by m2. Therefore, increasing m2 increases the net force. But just like with m1 and m2 are both moving. So both m and the net force increase. Now you might think that this means that since the net force increases and the mass increases, that must mean that the acceleration stays the same. However, it's important to note the relative increase in mass and force. If I were to double m2, let's put put numbers into this. Let's say that this is 4 and this was 2. If I double the net force, it goes from 20 to 40 newtons. However, the mass goes from 6 to 8 because this mass gets doubled, but this stays the same. So this doubling in force only results in an increase of about, in this specific case, about 1.3 of an increase. So the net force actually increases more than the mass does when I increase M2. So the net force, even though both the net force and the mass are increasing, the net force increases more than the mass does. So I'm going to end up erasing everything I just wrote. The way I would explain this in physics terms is I would say increasing M2 increases both the total inertia and the net force. However, the relative increase in the net force is greater than the increase in the mass. Therefore, the acceleration of the system is increased. So you might have to show this with work, but for the most part, that's kind of the setup. That's the way you would explain it. All right. Now we're going to do 35. So just like with 34, it's another conceptual question, but this time it's going to be modeling question 33 where we had friction. So pause the video, work itself, and we'll go over in a second. All right, now part A. Part A is a little bit different. So once again, M1 is going to change the increase and is going to cause an increase in the inertia. That doesn't change. So increasing F net does increase, or sorry, increasing M1 does still increase the inertia of the system. However, now we have two forces contributing to the net force: the friction caused by block 1 and the force of gravity caused by block 2. The friction is actually equal to Fn, mu Fn, or equal to M1g. So M1 is now increasing both the net force and the acceleration. Sorry, let me rephrase that. It's increasing both the net force and the mass. Now, I could do pretty much a similar logic that I did before and come to the conclusion that even though both of these are increasing, the mass is actually increasing more than the net force does. The mass increases, the net force actually decreases. So I apologize. Because these are in opposite directions, the net force, the increase in M1 actually decreases the total net force. So the mass increases, the net force decreases, which means acceleration also has to end up decreasing in order to balance this out. In order to make the left and the right balance, A has to actually decrease because of both of these. So the way I would explain is M1 increases the total inertia of the system, but also decreases the net force due to the fact that friction opposes the weight of M2, and the friction is actually related to M1. And then again, we find that the acceleration of the system decreases. Likewise, part B, honestly, the explanation is exactly the same. There is no difference when I increase M2 in the frictionless setup versus the friction setup. The only difference is that with not so much with increasing M2, but decreasing M2, which is essentially increasing M1. I didn't make the comment here, but in here, the acceleration can technically go to 0 because at some point there is a limit to when the static friction is going to take over, and this system can actually have 0 acceleration. In the previous case, when it was frictionless, regardless of how big M1 is, it was impossible to ever get the acceleration equal to 0. Here, it actually is possible. And that's it. That's all the multi-mass system setups. Like I said, we're going to be dealing with a few more examples in some of the later topics. But that was the pretty much, I would say, the spike for now when it comes to the modified Atwood machine. But notice that how the setup that I did for these questions was identical to what I did in the previous video about Atwood machines. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.